All right, so we talked about the idea that dystrophin is what it's doing is it's linking these muscle fibers together and providing lateral force transmission, which lets our muscle fibers work better, and it keeps the muscle fibers together so that there's less injury because there's less shear force. Okay, so if we look at this, and this is one of my favorite figures because basically what we're seeing is that if we look at dystrophin protein and we look in the TA muscle, which is it's in the front of your leg, that's your shin splint muscle, and your gastroc muscle, your MG, that's your gastroc, that's your calf muscle. If we look at dystrophin levels at the protein level in the adult, what we see is that the flexor muscle, your TA, actually has less dystrophin to start with than your extensor muscle, than the muscle you load all the time. And this is really interesting because when we do a lot of running, when we do a lot of training, we always get shin splints. We never get calf splints. We always pull our hamstrings and rarely pull our quads. We see the same relationship between the quads and the hamstrings as well. The quads have more dystrophin, the hamstrings have less. So that's really interesting. And then the second interesting thing is that when you get old, you lose dystrophin. And it doesn't get significant here in the gastroc, but it certainly does in the TA. And then the TA, you start with 50% of the dystrophin that you had as a youth, and then you lose another 50% of that. So we're getting even more likelihood of getting injured. And so what you look at the protein data and you say, oh, we must be losing mRNA for dystrophin. And as a result, we must be just not making as much. But then when you look at the dystrophin RNA, it's actually 2 to 3-fold higher in the old than it is in the young. And so what we have to have in order for these data to make sense, and you guys are probably already thinking this, is that there has to be a way that we're controlling dystrophin in a translational manner. Because the RNA is there, but we're not getting the protein. So we're losing something between the RNA and the protein. So what are we doing? Well, it seems that there's this microRNA that can bind to the 3' untranslated region of dystrophin, and when it binds there, it prevents it from being translated into protein. And when we look adult and old, what you see is, first of all, in the adult, the TA already has more miR31 than the MG. So we already see that there's more of this microRNA in the muscle where you have less dystrophin. Then when you look at the old, now what you see is that in both the old animals, or in both the old muscles, you can see that microRNA 31 is up 4 to 6-fold. And so we've got more RNA, we've got less protein. The reason we have less protein is because of this microRNA miR31. All right, so then that means that we're probably more likely to get muscle injury as we're older. And this is something that we hear all the time. If you're talking to an older athlete, they'll say, I do the same workout I used to do, but my muscles are more sore the day after, and it takes me longer to recover. Well, one of the reasons this could be happening is because we could be losing this ability to transmit force. The other thing that happens as we get older is we get periods of inactivity where we're forced into forced bed rest. So you have something go on, you go into the hospital, say it's right now, you have a period where you get coronavirus, you're going to go into intensive care for a week or 2 weeks. When you come out of intensive care, what happens at that point? And what we see is that older individuals don't recover as well. So what we did is we modeled this using rats. So you can do unloading in rats. So you don't put them into a hospital bed. You can hold their back legs off the ground. And then we do that for 14 days. And then after that, we do 14 days of reloading where they walk around and we see what happens. So the first thing that we see is that when we look at this marker here, and this is the flexor muscle, this is the extensor muscle like the gastroc. This is a plantaris muscle though. What you can see is that in the old, we have more of these centralized nuclei. And what centralized nuclei, you can see them here, you can see them all over in here. What they're showing is they're showing you muscle fibers that are regenerating because there's been injury and the muscle fiber is regenerating. What happens now when we look at, and then this protein, dysferlin, is a protein that's an injury-based protein. So when you injure muscle fiber, and specifically when you make a hole in the muscle fiber membrane, dysferlin goes up. And what I like to think of, it's like the little Dutch boy. You spring a leak in the dike, and the little Dutch boy comes along and puts his finger in the dike, keeps the dike from rupturing, and saves the whole village. Dysferlin is the same thing at the protein level. What dysferlin does is the little boy who puts his finger in the dike and prevents that opening in the muscle fiber membrane from actually causing the muscle fiber to degenerate. So now when we look and we do baseline 3 days and 7 days of reloading, there's no difference in dysferlin or in centralized nuclei in the older individuals. But now look what happens in the TA muscle. The plantaris muscle, again, it's like the MG, it has high amounts of dystrophin. We don't see any effect. But the TA, where dystrophin levels are low, you see this really big increase in dysferlin as soon as you start to reload. So you start to reload and suddenly your muscle has got more holes in the membrane, and so the result is that you need more dysferlin to fill them. The holes in the membrane are indicative of injury. There's an increase, a doubling of the amount of injured muscle fibers in the old. So then the question becomes, is that because of a change in dystrophin? So if we look at dystrophin protein, again, this is the MG, that's that calf muscle like the plantaris, where you see that there's no change in dystrophin protein. If we look at the TA muscle, in the adult, look what happens immediately after you do the unload. You go into reloading and suddenly you immediately make more dystrophin because you've gone from a period where you've got less loading, you're going to an abrupt change in loading, so you respond by quickly increasing dystrophin levels. Look what happens in the old animals. First of all, like before, they have half the protein. At rest, at the end of 14 days, they still have half the protein. But then here's the interesting part. During the reloading phase, they don't actually develop dystrophin until much later. And so this could actually lead to problems because you're walking around, you're loading the fibers, you don't have as much dystrophin. That could lead to increased injury rate. So is it again related to mRNA? Not at all. You can see in the MG, mRNA goes up in the reloading phase. TA, we had a 2 to 4-fold increase in the protein, no change in the RNA. So dystrophin protein is completely independent of dystrophin mRNA. So it's not something that we can just look at looking at the mRNA. What about this microRNA miR31? Well, in the MG, it stays fairly constant because that's the one where you have high protein levels, there's no injury. Look at what happens in the TA muscle. Here, what you see is that in the old, you actually have a spike. You have twice as much as in the young at baseline. The first day of reloading, you actually double that. It goes up to about 12-fold. It goes up to about 12 from about 6, so you double the amount of microRNA 31 you have. Here, you don't actually see it here, but you have a 30% decrease in this microRNA in the young. And so what we're thinking is that the young, it goes down, protein goes up. In the old, it goes up, protein doesn't accumulate, and it prevents that protein from accumulating, and it means that that muscle is now more prone to injury. All right? So that's all supposition, that's all, make-believe at this point. So what we did is we took a small piece of DNA that contained what we call a microRNA sponge. So remember what a microRNA is? It's 22 base pairs long, and it tries to bind to 22 base pairs that it matches with. And in dystrophin, it doesn't match perfectly, so it stops translation. What we did is we put in a lot of DNA that had a lot of microRNA 31 binding sites. And so when the microRNA binding sites are there, all of the microRNA 31 goes to binding the sponge, and none of it is left to bind to dystrophin. So what happens? And this is when we do a resistance exercise that's going to cause injury. You can see what happens to the protein here. When we inject the sponge, 7 days later, dystrophin protein is up almost 2-fold. And what does that do? Well, when you now do an eccentric load on the muscle, before, when you did an eccentric load on the muscle, you saw an increase in that dysferlin protein that was going to be associated with those holes in the muscle. You can see it here, that those holes in the muscle, you can see them because they turn green you can see that the fibers turn green. When we put in the sponge, we decrease the amount of injury we get, we decrease the amount of dysferlin we see, and so what we're seeing is that we've decreased injury just by increasing the amount of dystrophin. All right, so what I've shown you is that when we do unloading or reloading, old individuals lose more force than adult, and a lot of that is even though the same cross-sectional area. And so part of that is because the old muscles, or the old animals, are demonstrating a lot lower dystrophin levels during the reloading phase. That's because of this microRNA 31. And so microRNA 31 could be something that we could regulate that's going to increase or change the stiffness of the muscle, change the ability of that muscle to transmit force and protect our muscle from injury. So this is now a target for when we're trying to have an older athlete go longer into their career, or if we've got older people and we want to continue to have them continuing to be able to exercise at a high level. I've shown you that lack of dystrophin makes muscle more prone to injury. And then if I use a microRNA sponge, or if I create a way that I decrease microRNA 31, I can protect muscle from contraction-induced muscle injury.